Good afternoon, everybody. Thanks for the introduction. So I'm very happy and glad that I managed to be here, especially due to some travel-related issues. So I am happy that I made it. Very quickly, I will let me say something about myself before I start talking about memory corruptions. I'm Andrea Continella. I'm an associate professor at the University of Twente in the SCS group, which stands for Semantics, Cybersecurity, and Services, so quite a long name. And in SCS, I lead the cybersecurity team of the group. We do mostly research on two areas: data security. So there are colleagues that work on homomorphic encryption, applied crypto, privacy-preserving technologies, and system security, right? Which is the area, the research area that I like the most, the more technical and practical research in security. Myself, my research interests are mainly focused on three research lines: malware analysis and defenses, threat detection and response, and automated security testing and patching, which is, the research line that I'm going to cover in this talk. I'm also a big fan of CDFs. So I actually got in security through CDFs. Initially started playing with Tower of Hanoi and Macaroni. So I was very happy to see people around this morning and proud of their achievements. I also played with Shellfish, so the hacking team when I was in the US at UCSB. And now we also have a local team in Twente, THS, which is growing up very quickly, I have to say. All right, so enough about myself. Let's talk about memory corruptions. And, we already attended a nice talk from Richard that told us a lot about how to find vulnerabilities. Some of you might recognize this screenshot. Is about a paper that was published in 1996, very famous paper on smashing the stack for fun and profit. Basically, one of the first ones to discuss exploitation techniques for stack overflows, right? Back in the days where we had stack executable, no address space randomization, no control flow integrity, and so on. So pretty easy. 30 years after, we're still dealing with memory corruptions, right? And we see them, we constantly find them in even very large and popular software like Google Chrome, iMessage, or the Linux kernel. And of course, over these 30 years, obviously there have been a lot of changes. Likely we now have way more advanced and effective mitigation mechanisms that make exploitation quite hard, or harder than they used to be in the past. But we also have a lot of effort from the community to automatically find these vulnerabilities automatically, right? So we already discussed about AFL that was mentioned already in a few presentations today with its iconic UI. And this was a game changer, right? So in 2013, after the release of AFL, this bootstrapped a research line that was very productive, very engaging in terms of finding new approaches and new tools to identify vulnerabilities, mostly by improving fuzzing approaches, right? So we have seen many tools from the research community: Driller, Red Queen, A4, Cluster Fuzz, Pitch Fuzzer, AFL++. Great effort, tremendous effort from the community. Guess what's the result of these efforts? Crashes, right? Now we see a lot of crashes. We see crashes, and we report about potential vulnerabilities on any kind of software, and to the scale that now it's becoming difficult to track them. And I'll show you an example, right? This is a dashboard from the CSBOT system, which is deployed by Google to automatically and continuously fuzz the Linux kernel. So this automatically fuzz reports about vulnerabilities to the Linux maintainers, no stop. So 24 hours a day, 7 days per week. And this homepage shows some information about the latest results of CSBOT. We also see some details about the different images that have been tested. But if we look at the top left, we see that there are currently more than 900 open reports. So these are reports that potential vulnerabilities that nobody investigated yet. So we don't know whether we need a patch for this, right? And this is not also an isolated event, right? If you look at this dashboard over time, you'll see that there is always a very large amount of open reports that we simply, or the Linux maintainer simply did not have time to process and analyze. And we can see this also in this other chart, again from CSBOT dashboard, which shows the timeline for bug fixing. This is for the past 6 years. And the interesting aspect here is, again, on the top, if we look at these red dots, these indicate potential vulnerabilities or reports, crashes that have no fix after a year. And if you look at these red points, we can see that they are much more shifted toward the right side of the chart. Right? So this means that over time, there is an increasing number of potential bugs, potential vulnerabilities, and open reports that, again, we simply don't have time or resources to look at. So long story short, we do find nowadays, thanks to the developments and advancement in fuzzing and other techniques, a lot of security vulnerabilities, right, or potential security vulnerabilities. And these are great results, right? So as a community, we should be happy about this. This is pretty cool, nice achievement. We managed to move from a time where we barely knew about vulnerabilities and vulnerable software to a present that is overflowing with potential, vulnerability issues. So what do we do then, right? So what do we do now? Ideally, and that should be eventually our ultimate goal, we want these vulnerabilities to be patched. And given the scale of fuzzing techniques and the way we find new potential vulnerabilities, we need to start automating the patching process as well. Otherwise, we'll reach the point where the number of discovered vulnerabilities that are not fixed will still increase, and it will become even more unmanageable. And patching is a quite complex process. I would argue it's even more complex than finding vulnerabilities. So we need to decompose it, right? So we need to divide this problem into smaller sub-problems that we can start to address. So I see at least 4 steps in this, right? If we want to achieve automated patching. First of all, automated vulnerability analysis, right? So we need, in order to create patches for a specific software, we need to have a very clear and comprehensive understanding of what vulnerabilities we are dealing with, right? What kind of vulnerabilities are we talking about? What are their effects? What are their root causes? What is their severity? Only after we get such a comprehensive overview and also technical details, I would say, we can generate suitable patches. Once we have patches, we need to deploy these patches. And we will see in one scenario in this presentation that the deployment, the injection of the patches themselves is not always trivial as it might seem. And of course, we also need to make sure that these patches do not break the functionality of our software, right? So we will need to do much more research in terms of, patch testing and verifying that the new patches do not break the functionality of the programs we want to fix. So in this talk, I will. So each of these 4 steps are quite challenging, right? And this is something that we need definitely more research on in the next few years. I will just give you I will cover in my talk 2 of these scenarios. I will present 2 scenarios that we researched in the past few years that focus on vulnerability analysis and patch deployment. So let's start with vulnerability analysis, and in particular with what we addressed, which is out-of-bound write characterizations. So let's see an example, right? Few seconds here for people to spot a buffer overflow in this code. Good. All right. Let's see. So we have a function here that has some local variables. And if we look at the stack layout of this function, we would see something like this. So where we see our local variables for this function stored on the stack. Interesting part, we don't see here one of the variables, right? The PWOK is not actually placed in the stack, and this is a result of the optimization done by the compiler. So in this case, this variable is actually used as a flag in a register. And if we continue, we look at the rest of our of this example, we see here there is a buffer overflow because we are reading 48 bytes and we are storing them in a buffer in a variable that is only 32 bytes. What's the result? Well, this is going to overflow, and because of this stack layout that we have in this example, attackers might be able to affect the variable that is stored next to the vulnerable, let's say, buffer. So in this case, they might be able to override the real-world password buffer. Now, to characterize out-of-bound writes and understand a little bit better their effects, an interesting and important aspect is understanding which sources are potentially affected, which data structures are potentially affected by these out-of-bound write vulnerabilities, ideally at the source code level, right? So we try to research how can we extract insights about the overwritten, potentially overwritten data structures at the source code level as a result of an out-of-bound write. And if we want to do this, the first thing we have to do before characterization is recognizing, so detecting that we are dealing with an out-of-bound write. There are already existing and very solid tools for this. Of course, we have all kinds of sanitizers. I'm mentioning here two that we use for a comparison to our approach, ASAN and Softbound, but there are many others. The problem is that all of these approaches, all of these tools share some limitations. So first of all, they actually do not tell us which objects are affected by out-of-bound writes. So most of them are designed just to perform detection. Second, most of them, or some of them, do not detect intra-object out-of-bound write vulnerabilities, which can be as severe as well. So in this case, we're dealing with vulnerabilities that overflows, for instance, that occur between elements of a specific struct. And then finally, and most importantly, these approaches rely on heavy instrumentation. And we'll see now that these are some unexpected, or let's say, non-ideal consequences for our scenario. So let's go back to our example. So we have our original function, we have our original stack layout. If we compile actually this program, this function with ASAN, we get something like this in terms of stack layout, right? And then you start to see that it's something particularly different or quite different from the original layout. What we have here is that first we have red zones. And this is, of course, how ASAN works. So it inserts red zones to be able to detect illegal access memories. We also see that, for instance, here, the PWK variable appeared again. And we also see that some of these variables have been reshuffled in terms of order. So the message here is that if we now try to do characterization of out-of-bound write vulnerabilities using these heavy instrumentation-based approaches, we will get, non-valid insights, right? So in this case, in this example, we see that this buffer overflows does not affect the same variable as in the original layout. So essentially, we obtain artificial insights that do not hold in the real-world deployments. So in our research, we then designed and developed a new system that we call DVAC that instead focuses on characterizing out-of-bound write vulnerabilities in a non-invasive fashion. So here the goal is that we should not in any way affect the memory layout of the target program or its execution control flow. And also, as another advantage of our approach, it is also able to identify and track intra-object out-of-bound write vulnerability. So let's see first an overview. So we take as an input for our system a program together with its source code and a suspicious or crashing input. And as a result, we get in output, first, DVAC tells us whether this input triggers an out-of-bound vulnerability, so if we recognize the specific class of vulnerabilities. And second, it points in the source code which potential, which data structures could be overwritten by this vulnerability. So internally, before we reach this result, we execute three phases. First, some preliminary analysis where we basically build on top of LLVM passes to extract metadata and semantic information during compilation time and identify and discover write operations. Once we have this data, we can then do static analysis on the compiled binary, and we can match the extracted semantic information in the binary code, and we can create links between the LLVM IR and the binary codes. And then finally, we execute the program dynamically, and we leverage taint analysis and bounds narrowing to track writes, identify out-of-bound writes, and identify the affected data structures. So I'll go a little bit more in detail in some of these phases, mostly on the dynamic analysis, and now we actually identify and detect bounds for each write operation, right? Let's first start with what we used, what we defined in terms of write operation. So we defined and classified two types of writes. We have first independent writes, and these are basically operations that always write to the same variable. Right? So this is an operation where the destination address is computed or calculated within the instruction that is actually writing data. In this example, in this code, we see that we are writing into a buffer, and no matter how many times we call this function this write operation is always going to write into this buff local variable. Things are changed or different in case of dependent writes. In this case, we are dealing with write operations that might write to different variables or different objects during different invocations. So we see in this example that we have a string copy, and the instruction that eventually writes data in memory is going to write to a memory region that is pointed by a pointer that is passed as a parameter to the function. So if we call this function several times, every time we'll probably have different destination address for this write operation. So we apply two different techniques to track the bounds of these two type of writes. First, for independent writes, so what we want to do here is we want to find the intended destination object of a write operation. So we want to ideally move from the independent write to the correct and intended object in memory that is supposed to be write by this operation. So this is actually quite challenging to do, especially if we only look at the compile code, because we don't have any semantic information or other additional data that can tell us exactly the memory layout of this pointed object. So we use an alternative plan where we fall back to our LLVM intermediate representation. So by using debug symbols, we are able to map writes from compile code to the LLVM IR. And then from there, we can leverage the semantic information provided by LLVM to trace back this write operation to the destination variable. And then once we have identified the destination variables in the LLVM IR, we can map it back again, thanks to debug information, to the object in memory. And so we circumnavigated our issue, but we achieved our goal of understanding what is the intended destination object for a specific independent write. So we can now check whenever we find at a runtime an independent write, we can check whether the write operation that is being executed is actually inbounds for the intended destination object. Otherwise, we can identify that it is an out-of-bound write, and we can understand what is this write affecting and overwriting in terms of other data structures. Very good. Let's now see what we do in terms of dealing with dependent writes. And in this case, we rely on attaching bounds information to pointer, so that when we reach a dependent write, so as in this example we see here a dependent write, ideally we want to have attached to the pointers information that tell us what is the intended destination object for this write operation. And the way we do this is by tracking pointer creating instructions. So we have defined a set of rules to identify instructions in the compile code that basically create pointers. So this is a pointer birthplace. And when we find this instruction, we determine the pointee object information by the extracted memory layout. So we extract the information about the intended destination object, and we attach it to the pointer by tainting our pointer. So in this way, we can propagate this information with taint analysis through the execution of the program, and when we reach our dependent write, we can recover this information and understand what is the intended destination object for a specific operation. There is one more step. In fact, we also have to, in order to characterize and detect intra-object out-of-bound writes, we also need to deal with bounds narrowing instructions. So for instance, when we see that we are just getting access to an element within a struct, right? What we do in this case, again, we have some rules to identify bound narrowing instructions. And when we do so, we update our taint in our pointers to reflect the narrower bounds attached to these pointers. Very good. I hope you're still with me. Now we have a way, an approach to obtain from write operations information about the intended destination object of a write, and we can identify whether this write to be executed is actually inbound or not, and if not, what are the other data structures that are affected. So we built a system on top of this approach, as I mentioned, DVAC, and we evaluated our tool in two scenarios. First, on a synthetic dataset, so on a testbed that actually includes several combinations of out-of-bound write vulnerabilities, and on 3 real-world CVEs. And as you can see here in this table, in terms of being able to recognize and detect out-of-bound vulnerabilities, out-of-bound writes, DVAC outperformed ASAN and softbound. So we were able to detect more cases than ASAN and softbound. Most of them, some of them were also due to the fact that we do track and detect intra-object out-of-bound writes, while these other two tools do not. So that's one of the reasons why we have better, let's say, detection rates. On the other hand, we have, and DVAC has a little bit more in terms of false positive. It's kind of the price that we pay for this, but nonetheless, remember that these numbers in terms of detection rate or false positives are not actually the main advantage of DVAC. The main advantage, again, is it is non-invasive, which means that we can actually, even if this was same results, same detection rate, same amount of false positives, this gives us an advantage because now we can do and we can detect these out-of-bound writes with the same accuracy or even better, but in a non-invasive way. And this non-invasiveness allows us to obtain actionable and faithful insights about the affected data structures by out-of-bound writes, which is very useful for security analysts to understand and assess the severity of this kind of vulnerabilities, and potentially could be very useful for other automated pipelines that take these results and automate the patching process. All right, there is, however, a negative aspect. Nothing is perfect in life, and that is about overhead. So our approach actually introduced a higher overhead in comparison to other tools. Now, the next table I'm going to show you is a little bit scary. So hold your breath. We have a quite significant overhead in terms of execution time with respect to other tools, but there is a disclaimer. So our prototype is built on top of S2E, which is a symbolic execution framework, because initially we thought about using symbolic execution to track constraints that lead to write operations. Now, currently in our approach, we actually are not doing this. So we are not using any symbolic execution. We are abusing of a symbolic execution framework just for prototyping purposes. But our approach can actually be implemented by using a pure and, let's say, traditional taint analysis engine, which is what we are doing. So we are currently implementing the approach using libdft. And from our preliminary experiments, now the overhead is far, reduced drastically to 50 pair, right? Which is still more than ASAN and softbound, but it is now, acceptable and manageable. So this is mostly due to, a wrong implementation choice that we carried out during the prototyping phase. Summary so far regarding this part. So as I mentioned, DVAC is a new system that has the main advantage of being non-invasive in identifying and characterizing out-of-bound writes. Also, it gives us a little bit more detection rate because we can track intra-object out-of-bound writes at the cost of a little bit of false positive and higher overheads. And thanks to this non-invasiveness, we can now use DVAC to highlight in the source code the data structures that are potentially affected by out-of-bound writes, which is very helpful for analysts to, again, assess the severity or understand the identified out-of-band writes, but also we envision this to be used in pipelines that take these results and move forward to the goal of fully automating patching. Good. I mentioned then that I would present two scenarios, so we had one for now. Let's move to the second one, which is about patch deployment. And in fact, injecting patches can be actually way more challenging than it might seem, especially in some scenarios, such as when dealing with monolithic firmware images, right? So monolithic firmware is a specific class of firmware that does not present any OS abstraction, so we don't have any operating system. We have usually a custom format that mixes data and code together in a quite confusing or blurred way. And what we want to do here, what we try to do is investigating whether we can perform third-party patching on these monolithic firmware images without source code. So, and the scenario is, can security analysts or security operators inject patches in firmware of embedded devices, maybe critical devices that have been abandoned by the vendors because maybe they terminated their support period, or because simply the vendors, do not provide any patch anymore. This is particularly challenging because we don't have the source code, and mostly for three reasons that are very much, let's say, specific of this monolithic firmware image domain. First, we want to create a patch, and when creating a patch, we want to link this patch to a specific input that is the attacker input, right? So it's a source of input where the attacker can inject data potentially to trigger vulnerabilities. And well, in the monolithic firmware domain, we don't really have, well-defined sources of input. We have just, hardware peripherals that connect and send data, and that's kind of chaotic or hard to identify what's the real input, what is the input that we want, and what is the input that actually attackers can control for exploiting vulnerabilities. Second problem, now we assume that we have a patch, we know what's the input, where do we place our patch? We cannot simply, inject it somewhere and shift the rest of the code, as this would break all the pointers and the rest of the functionality of the firmware, especially when dealing with monolithic firmware images that have all these kind of custom formats. And second, we also sometimes have space issues. So these images are meant to be lightweight and small and efficient, and they often are stored in memory storage that are very small. So we have this kind of minimal embedded device where we might not have too much space to inject additional content, to inject additional bytes or code to patch vulnerabilities. And third, assume that we now have a location where to inject our patch. There is one more issue. This is most of these real-world images or firmware in general employs verification mechanisms. So they have kind of integrity checks that are executed at runtime when the firmware boots. So if we change anything in the firmware, well, this will invalidate the check. So we need to somehow take care of this. We build a system that we call shimware to address these issues. Shimware takes as input a firmware image initially and perform some preliminary analysis where we extract a control flow graph, we recover variables, we initialize states for some of these variables, and once we have a comprehensive overview of the firmware image, we can execute our three main modules, which are the IO finder, which will help us identifying IO sources, location finder, which will tell us what are the available memory regions to inject a patch, and self-check finder, which will tell us what are the portions of code in the firmware that execute verification or integrity mechanisms that we need to somehow deal with. Once we have all these three modules providing us some outputs, we can combine the results also with the help of analysis. We'll see shortly, and we can then package a new firmware image that includes a patch that analysts can provide. Let's have a brief look at these three components, starting with the IO funder. So as I mentioned, in the monolithic firmware image domain, we don't really have an abstraction of an operating system, right? So we do not have really standard APIs to rely on to track inputs, or sometimes we don't have even a concept of network, or we don't have a concept of a socket. We just have peripherals. And these peripherals communicate with the firmware running on the CPU via a memory bus. So how do we track or understand or identify input sources? Luckily, we can leverage the fact that the CPU uses memory mapped I/O to communicate with the peripherals, and that I/O memory addresses are usually defined as constants at compile time. So there are, reserved memory regions where we find all these pointers for memory mapped I/O that the CPU and the firmware uses to interact with peripherals and share data. So to track input and identify data sources, we can statically analyze the firmware image, and we can extract all the functions that use I/O pointers, so pointers is in the specific MMIO region. And then we execute these functions symbolically as follows. So whenever we find a read operation from I/O, we taint our data. Whenever we find write operation that write non-tainted symbolic data to I/O, that's where we found our output. When we find write operations that write tainted data to non-I/O memory, then this is our inputs. And again, if we find functions that eventually return some tainted data, we have again an input as well. Let me give you a high-level example just to make this a little bit more clear. Here we have a function. We see on the top there is an I/O pointer that we can recognize because it's a constant. It falls within the range that we assume to know. We execute this function symbolically. We see this pointer being used here. This is actually where the data comes in this function. We also see here that this pointer is used to read data and write data into a new memory region, right, in our local variable. That is a non-MMIO memory regions. So we can taint this data. We taint V1. We say this is potentially an input. And then we also find that this V1 is returned by this function. So we can now assume that this function is an input function. And indeed, this is actually what we found out in the example is an implementation of a getC, right? When we have a serial port and the device is through the serial port reading data and returning a character that is being read by the serial port. Good, so now we have a way to identify input sources. How do we deal with memory regions? So in this case, we do two things. First of all, we check for potentially empty space within the firmware image. So sometimes it happens that there are, contiguous memory regions filled up with zeros. It's not that common, but it happens. And if that's the case, we are lucky, we can use it, and that's great. In other cases, we also look for functions that are safe to be overwritten. So we basically, are removing code from the firmware to inject our own function. How do we do this? This might break, of course, the functionality of the firmware, where we look at functions that are not invoked by any other functions during the within the firmware, right? So we mostly do this statically, also with a little bit of symbolic execution. Of course, we also based on some assumptions and heuristics. But in general, we found that there are actually usually a few functions in firmware images that are not used by the firmware and that are left over of debug processes. So sometimes we find debug functions or other, again, functions that were used during the development or the debugging process and are not used in the runtime by the firmware. So we can override this function and we can inject our own patch. Finally, we also want to deal with integrity or verification mechanisms. So we need to identify self-checks. And we do this, again, in two stages. First, statically, by finding addresses mapped to, for code and page align within the image, the firmware image. So this is basically addresses that point to, within the firmware to portion of the code itself within the firmware. So that we call them self-references. And then we collect all functions that use self-reference or globals initialized to self-reference. Once we collect all these functions statically, we can then again resort to dynamic symbolic execution, where we identify among these functions those that we consider self-checks. First, when we find instructions that read from at least n locations inside the firmware, this is usually done within a loop. So we bound the loop execution within symbolic execution. And we also want to make sure that within the same loop, we do not have instructions that instead, write somewhere else. This is done to prevent, detection of functions like memcopy, which have the same patterns, right? So a memcopy also might be reading from code, but if this data that is being written is also read, is also written somewhere else, maybe this is not a self-check and it's not a verification mechanism that we have to deal with. Now, okay, we have all these three components together, so we can get outputs from all these three analyses. And what happens in the final component is that the analysts develop a small payload in C that provides to our system. We remove cell checks that we identify automatically within the firmware image. We use the largest region that we found where we can inject our patch. And also we provide the analysts with a few options for sources of input that they can choose from. So this part is not fully automated yet. And in the last component, Shimmer assembles basically everything together and provides a final patch firmware that is ready to be flashed. Does this work? Well, we tested it first on a synthetic dataset of 17 plus 50 firmware samples, and we found out that the I/O finder mechanism is actually quite efficient. We recovered successfully almost 250 useful I/O operations from these tested firmware images. We had 8 false negatives that were then solved by injecting or fixing some heuristics in our approach. And we also found that on average, Shimware found 375 bytes of available space for patching, which is not a lot of space, as you can imagine. So often in this case, you can really inject very minor patches like bytecodes that implement some check or boot the devices or does something else very minimal. In the best case, we actually found 70K of space, but in the worst case, only 28 bytes, which is, tricky to deal with to inject a patch and fix a vulnerability. We also tested this approach and system on 3 real-world use cases, so mostly for critical devices, so a power supply device, a PLC, and a pacemaker. And interestingly, when we were looking at this pacemaker monitor, we actually found a few critical security vulnerabilities, which are quite scary in the sense that it would allow attackers to bypass authentication, connect to the pacemaker and change the setting of a pacemaker. Luckily, this is done only via Bluetooth, so it's not done fully remotely, but it's still quite severe. And of course, we reported this vulnerability, and we also used Shimware to successfully patch this vulnerability. We also were in touch with the vendor, and eventually we saw that they replicated, they mostly followed our approach, or in general, the patch that they delivered was very similar to what we came up with, and also with our way of injecting the patch within this firmware image. We also tested a little bit the functionality of the pacemaker monitor after our patch, but again, then the vendor took care of actually releasing likely the final official patch. Last thing I want to say, maybe from a non-technical perspective before concluding this talk, is about dealing with vulnerabilities, right? We have seen this from a technical perspective, but there is also an aspect that I'm sure most of you are familiar with this coordinated vulnerability disclosure, right? So for all these cases, whenever we find vulnerabilities, we disclose this, ethically and responsibly to the vendors. And when I talk about coordinated vulnerability disclosure, people usually think, that's easy, right? So you just, send an email, tell people that they have to fix a vulnerability. Ideally, they fix it the day after, and all is good. Well, unfortunately, not in the real world, right? So things can go terribly wrong in this process, and it can be quite frustrating or challenging or hard to disclose vulnerabilities. So we also look at this process mostly from an ethical perspective and to provide guidelines for researchers and our students as well on how vulnerability disclosure should be conducted to make sure that vulnerabilities are patched ideally, but also that we deal with potentially sensitive information in an ethical way. Conclusions, takeaways, and main messages from this presentation. So Richard actually was mentioning that we now are in this age of vulnerability discovery, right? My feeling is we are quickly moving to a new age where we end up with discovering too many vulnerabilities. We are already finding too many vulnerabilities, and this will lead to kind of alert fatigue. So this is something that has been known already in the security community when we're dealing with, for instance, security operation centers. This is going to happen again and similarly in this scenario as well. So we keep finding more and more potential vulnerabilities that we cannot fix. So we really need, in terms of future research, to move more toward automated patching, which is a very challenging problem, and we need to decompose it. The first thing that we should do is properly characterizing vulnerabilities, or coming up with approaches to prioritize more severe vulnerabilities. This is something that we're starting to do. We started to do it with DBAC, and we're still working on it. And also, in this all end-to-end pipeline that we would like to have for fully automated patching, injecting patches is also a non-trivial aspect that we need to take into account. As you can imagine, there is much more in terms of research and things that we need to do in this direction. We're also starting a new project in this direction, also together with Herbert and VU. So we'll be also looking for PhDs very, very soon. So if anybody is interested, just feel free to get in touch. And with this, I'm done with the presentation and happy to take questions.